welcome. Today I'd like to go through a short webinar where we discuss some of the testing techniques that we use within our UK office. We've got a couple of main approaches. For general projects, we use a developer test framework, and I'd like to go over how that's set up and techniques of using it. And we also use a more formal testing approach, typically for safety systems, and this is using our TESI software for formal unit test. So in larger projects, sort of high volume commercial or safety critical software, we need to do an extensive amount of software testing. So in many respects, the only practical way to get around this is to use a specialist tool that helps you speed up this process. Now, for embedded systems, this can be quite difficult because we're very often intimately connected to the underlying hardware and have also restricted resources on the device. Therefore, we tend to use a specialist piece of software called TESI that was developed in the German automotive industry for testing small embedded systems. So in this case, TESI provides us with a complete development environment where we can design and specify our test cases, examine all of the underlying software on a module basis, automatically generate all of the test harnesses, and then either run them in simulation on the PC to give a sort of first approach to the software tests, and then download them onto our actual hardware and execute on the real hardware. So this gives you a fast and practical way to do a lot of unit and integration testing. Importantly, it also generates a lot of the documentation for you, and this greatly reduces the amount of workload. It's also very good for regression testing because it's able to cope with changes on interfaces, so changes on the functions as you go along. So it means that you spend all of your time concentrating on devising and executing the tests rather than writing all of the underlying software to conduct the tests. So again, if you have a large amount of formal testing, then the TESI software is a very good approach for small embedded systems. Also within our website, we have a large amount of resources devoted to it to show you how to use it. And it's also possible to get an evaluation license as well to actually try it out. The other approach that we tend to use for more mainstream and smaller projects is a form of developer test called test-driven development. So in this approach, the testing process becomes an actual part of the software development. So as we go along, the developer is generating test cases and then execute them in the debugger to prove that the fresh code that's been written will work correctly. And then we go through the process of developing new tests, adding the next amount of code and carrying on. So this gives us an iterative process where we build up and validate our software as we go along. So this is rather similar to possibly the way that you work at the moment, in that you write code, inspect it in the debugger to check that it's working, and then add some more code. But in this case, we're actually writing software tests, and as the code grows, so does the software test base as well. So we tend to spot unforeseen errors far earlier than we would through the inspection method, just using a debugger. So to use this method, we have three basic rules in that you're not allowed to write any production code unless it's to pass a software test. You're not allowed to write any more code than is sufficient to pass a software test. And you're also not allowed to write any more unit test code than is, you're only allowed to write a single additional test, and then write the code to pass that. So again, it's a fairly simple process. So this is actually zero cost. It's just a technique. So something that you can start to adopt and experiment with on your next project. So in fact, our microcycle means that we need to initially write a unit test, and then we build the code and run it to ensure that that test fails. We then add the minimal amount of application code to make sure that that test passes. Then we can run all of the tests to check that there's no other test that will fail. Once we've got our new code base, we can then refactor that and rerun the code to make sure we haven't done anything that will make the test fail. And then we go around the cycle again. So this is a slightly different way of developing code. And as I say, it makes software testing an inherent part of our development process. So at the end of our project, we now have a large amount of software tests that we can use for regression testing on future development of the project. So overall, there's been quite a wide adoption of this process in other areas other than embedded software. And various studies found that it does increase software quality. Over time, it helps with software integration. It also helps us get a faster time to market. We tend to remove bugs much earlier in the process, and you don't get into the nightmare situation of your code crashing because of some deep unforeseen bug in your software just a couple of weeks before you have to release it. And then when we come to reuse the software, it reduces the maintenance costs and helps us integrate and reuse software overall. So there's a link at the bottom here which gives an overview of various studies that have been run to see how test-driven development benefits software development. So in order to adopt this process, there are a couple of commonly used software frameworks so that we can start to easily add software tests to our projects. There's one called CPPU test, so this supports C and C++. And then a simpler framework called Unity, which is really aimed at C-level debugging. And it's Unity that we tend to use in-house as well. The advantage of this, particularly if you're working with Cortex-M-based microcontrollers, is this is provided by Arm as a software pack. So within the MTK pack system, we can simply download the framework and integrate it into our tool chain. If you're not using a pack-based development tool, then the website at the bottom allows you to download the raw framework so that you can manually add that to your project. Once you've added the Unity framework to your development tool, when you create a project, within the runtime environment, the testing utility will now be available in the runtime environment manager. So here we can simply select it via a tick box, and then it will be added to our project ready to use. The Unity framework will generally use printf to output test results. So this can be redirected through the compiler IO option to a number of standard out IO channels. So here we could direct it to a UART that's on the board so that all of our results will come out to a simple console window. But also we have the options for the debugger instrumentation trace. So again, this is part of the standard debug channel in Cortex M3, M4, M7, so that it acts kind of like a UART that's built into the debugger. So this will redirect all of the output from our test cases to a console window within the debugger so that we can then view and save the results off. This means that it will run on any hardware without having to use any peripherals that are on the actual device. Similarly, we can also use the event viewer. So this is an alternative I/O channel that will work on every Cortex-M device. So it also is the very small M0s, M0 Plus, which don't have the instrumentation trace. So whatever micro we're using, we can set up the test environment to connect to our debugger, so we can see all the results from our software tests. Once we've added the framework, there are also a set of templates that we can add that provide a framework for within which to develop our test cases. So here we've got a test main and then a test group runner, which we can expand with our individual test cases. So here at the top level, when we add the test main, we have a simple function call to call Unity main and tell it to run all of our tests. So this will call a sub-function where we can add various test groups to start executing. So here we're running a set of tests, look at a function called lookup, and another test group for our operating system threads. So then within each of these test group runners, we can start to build up test cases, which are a collection of tests for specific features within that software component. And then within each test case, we can build up a set of asserts so that we can, in this case, for example, we're calling a function, giving it an input value, and then checking that it gives a correct return value. And again, these asserts can be used in lots of different flexible ways. So in test functions, global data, and we'll have a look at how we can test operating system calls later on. We can also set up test cases to check failing values as well, so that we can prove all of the conditions on our code. And Unity provides quite a wide range of asserts for different C types, floats, integers, etc., but also arrays. It also provides asserts with delta values, so we can check that the output value is within a certain range. So again, this gives us quite a lot of flexibility within our test cases. Now, within the tool, rather than having to do the build, start the debugger, run the test cases each time and log off the results, we can add some simple scripts that will automate microvision, so that through one button click, it will automatically do a build, download into the debugger, execute the tests, and log the results. And this is quite important, that we can go around this adding code, building, running the test cases in a very fast cycle. And also, if we're using, for example, a trace tool, we can also log off code coverage results as well. So again, that further extends our testing capability. Now, when we are looking at developing software tests for our code, it's also important to structure our C code so that it is easy to test. So generally, this will very often mean developing a code in a layered approach, where we develop sections of our code as software components. So these are really like C libraries, so that we're placing all of the code that relates to one particular area of functionality of our code into a module or small set of modules. So this means that the C code is isolated from other areas of our code, so we can very easily build up a test harness around it. And ideally, it's also very much isolated from the underlying microcontroller hardware. So we should create a driver layer that is the only software that actually talks to the hardware. And then the bulk of our code is pure C code that really is making calls into the driver layer. So this by structuring our C code, we make it much easier to test. And in fact, by adding the test framework very early, and adopting a test-driven development approach, we can start to develop our software components within the test framework. So that as we go along, we're adding tests and then developing, adding code to our software component, checking that that builds okay. When we have a working component, we can start to integrate that into our main project. So it's again a slightly different way of developing code, but it does give us code that's much more portable. It's isolated from the underlying C code. It's very much more testable, very much easier to maintain and reuse on future projects. Now, the driver layer, as I've said, will basically be the layer that talks to the underlying hardware. And ideally here, we want to use a standard driver layer. And the one that's ready to go is the CMSIS drivers. So these are standardized drivers that talk to a wide range of common peripherals on a lot of microcontrollers. They have a standard API, so our component layer will be able to talk to them irrespective of the underlying microcontroller. And also they're developed for us, so very often they're included in the device family pack so that you can download them and start using on the microcontroller that you've specified. Also, the CMSIS drivers come with a driver validation test suite, so that at the beginning of the project we can select the CMSIS drivers that we want to use, bring up a test project, and then validate them on our hardware, either an evaluation board, and then migrate to our actual custom hardware. So this is, again, ready to go. It's very low cost to adopt, and it gives us confidence that we've got a working hardware very early in the project. And again, once we've set up the validation layer, we can execute it. The output is redirected to the console window so that we can run quite a large range of tests to validate the underlying hardware and our driver layer. And again, this can all be logged off as part of our documentation. Once we're familiar also with this process, it means that you can reuse it on any future project with any microcontroller that supports the CMSIS drivers. One of the newer CMSIS drivers is also a wrapper for our GPIO. So this is called CMSIS Virtual I/O or VIO. So this allows us a set of common functions that typically can be used to monitor things like buttons or LEDs on our hardware. It also supports analog I/O, so ADC and DAC. And it provides us a common API to control all of those features. But inside the VIO, we can very easily switch off access to the real hardware. And then inside the CMSIS VIO driver, it has a set of memory locations which act as virtualized memory for our GPIO. So this again also makes a very good test target that we can write to the simulated GPIO rather than the real hardware. So we can read and write within our test cases and simulate button presses or switching on of LEDs or reading ADC or DAC data. So again, adopting this makes reusing test cases very much easier. Again, as we're structuring our project, as I mentioned before, typically this now means that we will end up with a range of projects. So at the top here, we might have our main application project, which we're developing, but we can build our software components in a set of sub-projects. So this is just the code for a specific software component. So in this case, we're looking at the code to read an external GPS unit, and then we can build our test framework around that. and indeed we can develop the GPS component within this sub-project. And the GPS component is using the CMSIS UART to talk to the external GPS unit. And at the bottom there, we have the test project, which is the validation framework for the UART, so that we can run the test framework to check that our hardware is working before we integrate it to the component code. So here we have a hierarchy of projects that are testing the board layer, the component layer, and then integrating into the final project. And if we discover any problems at any point, we can fall back to the sub-projects to try and resolve the problem. So again, it gives us more options within our debug environment. Another thing that we'll have to do, particularly as more and more people are adopting a real-time operating system, as well as testing C code, we'll also need to test our code at the RTOS level as well. And this gives us a lot of opportunities because the operating system threads have got very well-defined I/O input and output channels, and these can be used for our test framework. So for example, we have 3 threads, a transmit and receive thread, and also a clear thread. So the transmit thread is sending a pattern through a mail queue to the receive thread, which is then writing that pattern to an LED port. When we want to clear it, the transmit thread is sending an RTOS signal to the clear thread, which will then switch off all of the LEDs. So again, a very trivial project, but when we come to test that, we can create a dedicated test thread, and we can switch off the TX thread. And now the test thread can write into the mail queue and signal and also generate signals as part of its test code. So again, we can write patterns into the mail queue, run the RX thread and see how it performs and check that it writes the right pattern to the LEDs. We can send a signal to the clear thread and then check that all of the LEDs are switched off. So testing at the RTOS level, it really is quite nice because we have these objects with these very well-defined I/O channels that we can then test against. So again, in our test framework, we'd add another test group, and then within our individual testing threads, we can build up some C code to start a thread that we want to test. We can set an RTOS signal, for example, have a small delay so that the code gets to run, and then we can check the port patterns or whatever we need to validate within the RTOS thread. Once we've finished the test case, we can simply then kill the operating system thread. So this gives us quite a nice way of building up and controlling operating system threads and checking that they're running correctly. Now, when we are testing on the hardware, we've got a choice of various debug adapters. But within the MDK, there's a debug adapter called the ULINK Plus. So this has a fast download time, but also it has a built-in logic analyzer that gives us dedicated digital and analog I/O channels. So this means within our test cases, we can generate a hardware in the loop testing. So the ULINK Plus can set digital I/O or set analog voltages onto our hardware before we run the test case. Similarly, if we're generating an analog output, we can read that and check that against an expected result as well. So the ULINK Plus gives us quite a lot of new possibilities within our testing framework. And again, this is really a fairly minimal cost. Now, some newer approaches that are coming along is the Arm virtual hardware. Now, we'll be running some webinars on this in the near future, but to give you an overview of how this is used, Simply, ARM have a number of CPU simulators for their Cortex M3, M4, M7, etc. And these simulators have a subsystem of built into them. So things like DMA, a virtual socket interface. And on top of this, there is a virtual streaming interface, which is effectively driven by Python code, so that we can have a file, for example, of sensor data. And then as we run the simulation, that sensor data is input into the simulation model. So this allows us to develop a hardware abstraction layer, so that we have streaming interfaces, virtual socket interfaces, and CMSIS driver type interfaces that allow us to create a development environment that is divorced from the final microcontroller hardware. So we can develop a lot of code within simulation and also start to build up our test-driven development tests against the simulation model as well. So we can start to develop a lot of our code before we even have our real hardware ready. And then as we go through the project, we can develop in simulation with our virtual drivers, and then migrate these out to an evaluation board. And then eventually, when our custom hardware is ready, we can go out to the final target hardware. So this allows us a lot more flexibility in development. It also sits into a more modern development process where we can develop in our IDE, test against our simulation model, and develop our test cases. And alongside that, we can then use that same model and test base for continuous integration and even continuous deployment. So these are new sort of development processes that we'll be able to adopt now and in the very near future. And again, in our future webinars, we'll show you exactly how this works, again with the current Microvision 5 and also the newer Microvision 6. So thank you for your time today. I basically will post up this the webinar and this recording. We've also have it written up as an application note. We'll point you at the software pack so that you can download and experiment with Unity. And we have some example projects that will help you get going as well. So again, shortly after this webinar, next couple of days, we will send you out a link to these resources. If you have any questions about what we've got today, please raise them at the end here and I'll come back to you after the webinar. So now I'll hand back to Wolfgang, who'll croak his way through the closing phrases. Thank you very much for your time. Cheers.